What levels of temperature and carbon dioxide have we had on Earth in the past?
We get a record of Earth's past climate and atmospheric composition from the analysis of water and air bubbles trapped in ice cores drilled out of the Antarctic or Greenland ice caps, for instance. It is found that the Earth goes through warm and cold cycles over scales of 100,000 years. Why is this? The ellipticity of the Earth's orbit around the Sun implies that the Earth-Sun distance changes by about 3.4% during the course of a year. Gravitational interactions with Saturn and Jupiter cause this ellipticity to change with a periodicity of about 100,000 years. When the orbit is more circular, the summers are just cold enough that the snow and ice from the previous winter don't melt. They begin to accumulate, increasing Earth's reflectivity, and the Earth gets colder. This idea that a small change in ellipticity can have a significant effect was proposed in the 1920s by a Serbian scientist, Milutin Milankovic. It was pretty much dismissed at that time. Another effect is due to the tilt of the Earth's rotation axis, varying over cycles of 41,000 years. A greater tilt leads to more extreme seasons. The effect is greater at higher latitudes. A smaller tilt means milder seasons, warmer winters and cooler summers, contributing over time to a buildup of ice and hence cooling. Further, there is a wobble in the Earth's rotation axis, and that wobble has a trend over cycles of about 26,000 years. The wobble is due to tidal forces caused by the gravitational influences of the Sun and the Moon that cause the Earth to bulge at the equator, affecting its rotation. The sum of all of these individual effects is that the Earth goes through warm and cold cycles over periods of 100,000 years. The Earth's temperature history can be charted in various ways, and a consensus emerges. But how do we get the temperature and carbon dioxide history of the Earth's atmosphere from ice core data? This is done by looking at isotope abundances. Oxygen is one of those elements that has isotopes. That is, it exists in configurations that differ in the number of neutrons in its nucleus. It turns out that isotopes of various elements play an important role in paleoclimatology, helping us trace the history of various processes on Earth. So, for oxygen, the usual isotope has 8 protons and 8 neutrons, and so an atomic mass of 16. But there is a reasonably abundant, heavier isotope of oxygen that has 8 protons and 10 neutrons, so an atomic mass of 18. This means that there are also two kinds of water molecules, one that has the lighter oxygen in it and the other the heavier. Water molecules are constantly jiggling around, but the lighter ones jiggle a little bit faster and evaporate from the ocean just a little bit faster than the heavier ones, and the degree to which they evaporate faster depends on temperature. So the ratio of oxygen isotopes in water vapor and air, and ultimately in the ice core formed from that water vapor when it precipitates, can be used as an indirect measure of temperature. Water vapor also has differing amounts of dissolved carbon dioxide in it, from which the carbon dioxide abundance through history can be determined. One can literally see the year-by-year melting and depositing of ice in ice cores over 3.5 kilometers deep in ice that fell up to 800,000 years ago. Such observations reveal an increase in carbon dioxide and temperature beginning in the 1900s, and it looks different from any previous warmings. Such a rapid increase has never been seen before. In addition, we can look at sediments and deep sea cores around the world, which give us the history of water temperatures taking us back 1 million years. Planktonic and benthic, that is floating in water or bottom-dwelling, shelled organisms like forams and diatoms have shells made up of calcium carbonate and silicon dioxide respectively. The carbonate found in many common geological features such as the White Cliffs of Dover were once at the bottom of the sea. As these organisms die, their sediments get buried and preserved. The chemical makeup of the shells reflect water chemistry at the time of shell formation. Oxygen isotope ratios contained in the shell can be used to infer water temperatures. Shells grown in warmer waters will be enriched in the heavier isotope of oxygen, as the lighter isotope will evaporate more. The change is only tiny, 0.2 parts per million decrease in the lighter isotope for each degree of temperature increase. Yet, this is sufficient for scientists to be able to estimate the temperature of water in which the forams lived millions of years ago. Warmer weather within limits will cause organisms to proliferate, as there will be more nutrients from the extra weathering of rocks on land. Since each species has a particular set of ideal growing conditions within a limited range, their relative abundance is also indicative of prevailing conditions. All these effects can be studied. The important thing is that the detailed study of deep ice cores and deep sea sediments paint a consistent picture.